Okay with the lighting? Okay. All right, so last class we started the double integrals. We did double integrals over rectangular regions, which we said were kind of the easy case. And then we did these type 1 regions. Type 1 regions looked like any region where your y coordinates were stuck between two functions of x and your x coordinates were bounded between two constants. And had I assigned you some homework out of there? Any questions on that? Anyone? All right. So we did a couple examples in class, and we stopped when we got to type 2 regions. There we go. So the difference between type 1 region and type 2 region is just that for type 2, your y values are stuck between two constants, and your x values are stuck between two functions of y. So you use this whenever your curves fail the vertical line test, but they pass the horizontal line test. You would use like a type 2 region. Now, if this is the case, that we have type 2, we're going to use C and D instead of A and B for our restrictions on y. And our x values are going to be now stuck between two functions of y, which we're going to call h1 and h2. h2 is the one further away from the y-axis. h1 is the one further in. If you compare that to type 1, we had G1 was the one on the bottom, G2 was the one on top. Now, if we have that, then our double integral over that region D of the function with respect to area is integral from C to D, integral from H1 to H2 of the function. Then notice your order of integration, dx dy instead of dy dx the way it is with type 1. Can I switch this order of integration? No. Only if this is rectangular, right? So basically, if both of your integrals are restricted between two constants, you can flip the order of integration, but in general, no. So here's our example that we're going to start with. And I'm going to do it, and then we'll come back and take a look at the picture. So find the region bounded by, or find the double integral d of xy dA, and the region we're bounded by y equals x minus 1 and y squared equals 2x plus 6. Now remember, the region, right? The region that we're talking about is just the ground, right? That's the part, that's our domain that's going to be plugged into a surface, and we're trying to find the volume below that surface down to our region. All right, so keep that in mind. That's what we're doing. The function that the surface we're looking at is actually the surface xy. That's the thing hovering above our region here, and it could be below, right? Could actually go below, but our first picture, our first idea we ever did of this, we always assumed the surface was on top. So we're going to start out by drawing the region, right? And that's going to be part of what you get credit for on any test you take, any quiz you take home, is drawing an accurate region. So y equals x minus 1. This is a line, has a y-intercept of -1, and has a slope of 1. So we're looking at something like this. It's pretty good if you ask me. It's a pretty good line. And then the other one is what? We have y squared there, right? So you could maybe solve this for x. All right. First, you move the 6 to the other side, then divide by 2. X equals 1/2 y squared minus 3 is going to be a parabola that opens sideways, right, to the right. And it's actually been shifted because of the minus 3. It's been shifted which way? To the left 3. So it'll look something like 1, oh, I shouldn't say that's 1. It's probably 1, 2, 3. So it'll be something like this. So that's our region in here. Type 1 or type 2? Or is it a rectangle? Well, it's not a rectangle, right? Why is it not type 1? Yeah, if I try to come in here and draw like my little arrow that goes for the bound on the y coordinates, the curve on top and the curve on bottom are the same curve, so it would fail. I wouldn't be able to do it. So I'm forced to go the other way, like this. And no matter how I draw this line, I can move it all the way up or all the way down through this region. It's always stuck between the line and the parabola. So this is definitely going to be type 2. If it's a type 2, we need to come up with our h1 of y and our h2 of y. And so if we look at it, the h2 will be the one to the right, the h1 will be the one to the left. So you have to figure out what the line and the parabola are, you know, what their equations are if you solve them for x. We already did that with this one right here, right, the parabola. We have not done it for this one. So we need to solve that for x, and we get what? Y plus 1. So this one is just x equals y plus 1. So what is h1 of y then for us? 1/2 y squared minus 3, right? So this one right here on the bottom is h1 of y. Then h2 of y will be the linear equation, which was y plus 1. Anything else we need? Yeah, our bounds on y, right? Our, you know, where's this region starting and ending in terms of the y variable? So don't we need to know that y coordinate of that point of intersection and that y coordinate of that intersection so that we can get our C and our D? Yes? So to find the points of intersection of two curves, you set them equal to each other, right? I have both of these solved for x, right? So if they're both solved for x, I just set them equal to each other. So for the intersection, I'm going to get y plus 1, set it equal to 1/2 y squared minus 3. We'll move everything to one side. Let me see, minus 4 equals 0. That's a quadratic equation. We could solve that, right? If I was going to do it, I would just multiply everything by 2 first because I think it's going to factor. I don't like that fraction out front. So I scaled everything by 2, And then, yeah, that makes it a little more obvious that that factors to be y minus 4, y plus 2. So our two solutions are 4 and negative 2. And those are our solutions for y, right? So our C and our D are given to us by those. Let's just make sure we get the proper order. You know, C is the lower one, D is the taller one or higher one, so it's the greater one. So I'm ready to write my answer down. I have the integral, double integral. Did I put the double integral up here? I did, okay. Double integral over D of xy dA is going to turn out to be the double integral. The first one will go from, first integral goes from negative 2 to 4. Now the inner integral is my h1, h2, so h1 was 1/2 y squared minus 3 up to y plus 1, right? So h1, h2. And then in here is the integrand itself is xy, right? That doesn't change. That was given to us in the problem. So that's the surface. And then we have d dx dy. That's the setup right there. Do you want to go through the evaluation of this, or do you want me to move on? It's kind of up to you. I don't care. How many of you want me to just take this the whole way through? Yes? Okay. All right, so what I'm going to focus on first is the integral, right? I'm going to do that one first, but I'm going to carry the notation the whole way. So I'm going to keep the outer one there the whole time. Some people like to take the inner one and go do it separately and then just come back with the answer. Either way. Just if you're going to do it separately, just go onto a different side of the paper and do, you know, and then bring it back. Ah, shit. Oh, that hurt. Damn. Son of a bitch. Let's cancel class. Oh, man. Here you go. Do attendance again. All right, so the inner integral I take the antiderivative of x times y with respect to x, so treating y like a constant. So what is the antiderivative of this then? X squared y over 2, or you could say 1/2 x squared y, either way. I'm just going to put 1/2 x squared y. But then we need to evaluate that from the y plus 1 and then the other one. But what am I going to replace with y plus 1? The x or the y? The x. I'm replacing x with 1/2 y squared minus 3. I'm replacing x with y plus 1. How do I know I'm replacing x? Because I integrated with respect to x. So I'm treating x like the variable, so it is the thing that gets replaced. My next integral, the outer one, I'll do the y. Close it off, dy. Again, you may wish to do this elsewhere. Later on, when we get to triple integrals, we're going to have 3 of these. So we're going to have like an inner, a middle, and an outer. So you may not want to be carrying the outer and middle with you the whole time. So you may just want to go do the other one somewhere else. getting ready to drop some students for attendance, so I want to make sure I have it documented before I do it. Kind of sucks to get dropped if you're passing but you're not coming to class, but I don't make these videos so people don't show up. Thank you. Think you're all in good shape, right? All right. So we plug in. Oh man, seriously, we got to do this, I guess. -2 to 4. All right. Let's plug in for x, y plus 1 first. And I have to plug it in right there, so I have to square it. So 1/2 y plus 1, I've got to square that. Then I still have times y next to it. Then minus, now I plug in the other one. So 1/2, now I plug in 1/2 y squared minus 3 squared times y again. And then all of that dy. Does everyone see that plugged in? Replacing the x right here with y plus 1, that's this. Then subtract from that, replacing this right here and here for x. This is just algebra at this point, right? Just expanding things out. So equals integral -2 to 4. All right, if I expand this and then multiply by y and then multiply by 1/2, I get 1/2 y cubed plus y cubed, I put y squared, y cubed plus y squared plus 1/2 y. Do y'all agree with that? So this right here, y plus 1 squared, is y squared plus 2y plus 1. Then times this is y cubed plus 2y squared plus y, and then half of that is this. So, and then over here, this is not so fun. I'm going to have to write this one down. This is going to give me 1/4 y to the 4th minus 3/2 and 3/2 added together is 6/2 is 3 y squared plus 9. Is that right? 3/2 minus 3/2. Yes. That's just this squared. Then times y, then times 1/2. So, and then subtract each one of them. So this is going to become minus 1/8 y cubed plus 3/2 y squared minus 9/2 y. Pardon? Yes, why didn't I put that up there? Oops. This was up here 4th and squared, right? Okay, and then come in, this will be 5th, and this will be 3rd, and this will be just 9. That's it, right? And I changed all my signs, so I think I'm there. dy. I would expect that, you show more work if, you need to do that. I mean, I'm just trying to go quick here. I'm trying to do as much of this in my head, but I leave myself open to errors that way. And now you can combine like terms, right? So equals, let's see, -2 to 4. All right, I'm going to put this in descending order. I have -1/8 y to the 5th. See, cubes, I got 1/2 y cubed and 3/2 y cubed, so that's 2y cubed. Squares, I only have 1y squared, so plus y squared. And then minus 4y dy. Now you're just back in Cal 2. I was saying Cal 1 last time, right? Back in Cal 2, you integrate that, just normal integration. Power rule. So equals 8 times 6, 48. So 1/48 y to the 6th plus 1/2 y to the 4th plus 1/3 y cubed minus 2y squared, evaluating -2 to 4. Now you just plug 4 in, right? And subtract what you get when you plug in -2. Going to ask for help here. I just don't feel like doing that. That's tedious. Let's try this. Make this a little bigger. My inner integral, right? My inner one went from negative, what was it? Negative 1/2 y squared, right? So y squared, oops, negative y squared over 2. That's negative 1/2 y squared minus 3, all the way up to, what was it? Y plus 1? Y plus 1. And I was integrating x times y with respect to x first, right? Is that what we had? Oh, this was positive right here? Okay, yeah, that'll make a difference. Is that what we had? I don't know. No, it was y squared, yeah, because it went that way. Is that what we had? Yes? And now if I just integrate that answer with respect to y, I get that. Is that what we had? Negative 1/48 y to the 6th. Yes, I'm asking, yeah. So, and then now you plug in. So what I can do is I can take that answer. You know, this too much. Let me just do this. Did anyone get a numeric answer yet? Trying to just get you an answer here. -2 to 4. 36. Anybody get 36 that tried it? No? Did anyone get an answer? It's okay if you... Should I go through the answer or not? No? Okay. It's looking like 36 should be the answer to this. All right, any questions on that? Now, the geometry of what happened there, we had our region on the ground, right? Over here, kind of tough to see that. I can't tell what you can see here. I can't really see that. There, now you can see it better, but this is looking from the top, and we've got a surface that's x times y, that bluish surface. We've got a region on the bottom. So if we go ahead and take that surface out, then you can kind of see that solid in there. Do you see it? We found the volume of that solid to be 36. Find the volume of the tetrahedron bounded by this. So we need to talk about a tetrahedron first, like what a tetrahedron is. Kind of like a pyramid. Kind of, you've got Let me show you what the tetrahedron is. That's a tetrahedron right there. So how many sides do you have here of this tetrahedron? There's 4 of them, right? So you've got like a base. You've got 3 sides. They all come to a point. So you could do some sort of pyramid, but the base of this tetrahedron is a triangle. Or you could say that all sides are triangles, right? All sides are triangles. So we're trying to find the volume of this. And that's all the information we're given. So let me write down tetrahedron bounded by x plus 2y plus z equals 2. X equals 2y, x equals 0, y equals 0. So I'm going to, again, start by trying to draw a picture of my region on the ground. So this tetrahedron has these 4 conditions on it, right? So let me try and see if I can figure out what the heck this looks like on the ground. What is this geometrically right here? X plus 2y plus z equals 2. What is that a picture of? It's a plane, right? Remember our old equation for a plane? AX plus BY plus CD, or plus CZ plus D equals 0, equation of a plane. Actually, what's the normal vector for that plane? 1, 2, 1. Not relevant to the problem. I'm just making sure we remember that. That's a plane. This is actually a plane also. In 3-dimensional space, it's a plane. Right? You can move everything to one side. You would just have your normal vector on that one would be 1, -2, 0. This is also a plane in 3-dimensional space. This is also a plane in 3-dimensional space, right? X equals 0 is the YZ plane. Y equals 0 is the XZ plane, isn't it? In the very beginning of this class, we talked about, what space are you in? Are you in R2? Are you in R3? It depends. Different things look different in different spaces. But I'm trying to draw what's on the ground. So if I'm on the ground, X, Y, then Z is what if I'm on the ground? Z is 0, right? If Z is 0, then this equation right here becomes a linear equation in 2 variables, right? Which is a line in 2-dimensional space. This right here doesn't even have a Z in it. That is also a line in 2-dimensional space. This right here in 2-dimensional space is a line. This right here in 2-dimensional space is a line. So what I'm going to do is draw all those lines in 2-dimensional space and then talk about, the rest of it later, all right? So starting with this one, if Z is 0, we get X plus 2Y equals 2. How would you go about graphing that line? I mean, what's your method? Do you do like Y equals MX plus B and draw a line, or do you do X and Y intercepts? Like, do you have a preferred method? No? Intercepts? That one would probably be pretty easy with intercepts. What we mean is what? Let X be 0, then what does Y have to be? 1. So I know that at this point, if X is 0, Y is 1. That point lives on that line. Now, why did I put that? I have no idea why I put that. I meant to put that. If Y is 0, what's X? 2. So we have something like this. Okay. That is this one on the XY plane. So that plane right here, comes through and cuts through our ground through that line. Yeah? X equals 2Y. That one you can't use the X, Y intercepts because the X and the Y intercepts are the same. It's 0, 0. So the only way you could really do this is to rewrite it as y equals 1/2 x, and use the fact that your slope is 1/2 and your y-intercept is 0. So starting at 0, as a y-intercept, go up 1 and over 2, right? And then graph it. To say my lines are pretty good today. Now right there, just those 2 lines, I'm not enclosing a region yet, right? I have 4 like sections that it could be. The next 2 pieces of information are going to give us everything else. So x equals 0 is vertical line. Y, it's the y-axis, right? That's this. And then y equals 0 is the x-axis. Was it z equals 0? Oh, it was z. I was just about to say, wait a minute, I just made 2 regions. Thank you. Z equals 0. So what is z equals 0? Everyone catch that right there? Z equals 0. I accidentally wrote down y equals 0. What is z equals 0? Yes, but we can't graph it here, right? Z equals 0 is the xy plane. It's actually this sheet of paper, isn't it? So remember this, we're looking for the tetrahedron that's bounded by those things up there. One of them is the ground. Z equals 0 is the ground. Then you have the plane coming through, right? And then you have x is 0 and z is 0 are 2 other planes. X is 0 is another plane. So you imagine that, maybe I did it good in my picture here. Wish I could take my surface out. I don't want it there. Oh yeah. Looking from the top, right? That's what we have. So x equals 0 is the YZ plane, which is this plane right here, right? X equals 0 means the y is free, but in 3-dimensional space that comes up at us, doesn't it? And goes into the board. And then the other one, y equals 2x, or x equals 2y? Was, which one was it? This one, right? It was this one? X equals 2y. Since the z is not in the equation, the z is free, isn't it? So this plane right here comes straight up, straight out at us, straight into the board. This one right here does not come straight at us, does it? That's a plane that's coming at an angle and slicing through. So when we put all those together, the one coming straight up at us, this one coming straight up at us, and that angled one, we get this. So one side straight here, turn it the other way, it's straight there, but then that other side is the curved one. Do you all see that? All right. Back to this. So here's my region of integration right here, the region. What type region is this? Type 2? Type 2 would mean that we want to go this way, right? Do y'all want to go left, right, like this? Could we do it that way? Well, the blue one is on top of the green one, right? But then halfway through, what happens? It switches from the red one and the green one, doesn't it? But could we do that? Yes, we could. But wouldn't a type 1 be a little more efficient here? If we go type 1, then as we move that left and right, we're always going to have the red on top and the green on bottom. Yeah? Let's take a moment to label these things because we never did. This one on top was the, x plus 2y equals 2. The blue one on the bottom was y equals 1/2 x. Do we know our restrictions on x? Because this is going to be type 1, we are going to want restrictions on x here. What do they look like because my picture is so good? It looks like 1, right? But you wouldn't know that until you did what? Set the two equal to each other? So we would have to verify that. Now, because I'm going type 1, right, because I'm doing type 1 here, I do need to solve this one right here for what? For y. So solve that for y just so we have it. Y equals negative 1/2 x plus 1. Set those two equal to each other just to make me feel like we are complete. If we set negative 1/2 x plus 1 equal to 1/2 x, well, that's pretty clean, isn't it? Add the 1/2 x to both sides and you get x equals 1. It's pretty straightforward. So that is 1 right there. I am happy about that. The left end of that interval is going to be 0. Do we have everything we need? Set up the double integral? You've got your limits of integration? No? Type 1 region, here we go. We're going to go integral from what? Double integral 0 to 1, then from y equals 1/2 x, right? Up to the other one, which was negative 1/2 x plus 1. Right, that's both of these. The one on top was the red one, that's this one. Bottom one was the blue one, that's this one. Now what? What's that? Yeah, what's f of xy? What is the thing you're trying to find the volume under? That plane, right? It's that one plane that came in cutting at an angle. You want under that, right? So go back up to that plane. Could you solve that for z? If you solved it for z, then wouldn't z be a function of x and y? Wouldn't it? That's exactly what we'll do. So kind of at this point, we're saying to ourselves, this f of xy that we want to integrate, what is it? You know, what's the surface that we're trying to look under? It's the plane. So because this is the plane, it needs to come from this equation. X plus 2y plus z must equal 2. Right? I don't have to fix z. I'm not saying z is 0 anymore because I'm not looking at the ground. I'm actually letting the plane be what it is. It wants to be a plane. So doing that, solving it for z, we get z is equal to 2 minus x minus 2y. Now z can be determined completely from x and y. So it is a function of x and y. And that will be my function that I'm putting in here. Does that make sense geometrically? Trying to find the volume underneath that plane, but above that triangle on the ground. D what? D what? dy dx. So I'll just write the last integral and then we'll be done. Integral 0 to 1. Integral 1/2 x to negative 1/2 x plus 1 of 2 minus x minus 2y dy dx. That's the integral that we would have to evaluate. Y'all agree? Any questions? Do y'all want to know what the value of it is or no? You think you would actually try that one on your own? Will Wolfram Alpha do it? Double integral? Definitely, yeah. You could do, let me see here. I don't know if I can connect in here. See how long it takes to connect. We'll try it. I haven't done a double integral with Wolfram Alpha in a while, but I'm pretty sure it'll do it. Come on, you can do it. Secure logon. So let me see. Integrate. What was it? 2 minus x minus 2y from 1/2 x, so x over 2, to negative x over 2 plus 1. Right? So that's the first integral. Let's see what it does. See, good. It said dx. Is that what we wanted? Did we want it with respect to x? No, we want it with respect to y. Respect to y. Let's try that. Probably. Yeah, that's what I was going to do, dy. That took a long time. All right. Seems like it handled it, right? But then you'd have to maybe do this. Watch. Because you have that answer, right? If it's real nasty, you have to type it in. So why don't I do this? I'm going to put parentheses around this, right? And that right there I want to integrate, don't I? I want to integrate that dx from 0 to what? 1? So I'm going to integrate an integral. Oh, we did it. Numerical answer would be nice here. There we go. 1/3. Now let's see if Mathematica agrees with that, because I'm a little skeptical. So I'm going to do double integral. Blow this up for you. Crap. Okay, so we go 0 to 1, x over 2 to negative x over 2 plus 1 of 2 minus x minus 2y with respect to y with respect to x. Okay, worked. Yeah, so either way, you can check your answer, I guess. You should get 1/3 here. All right, let's look at another example. This is a good one. I like this one. Find double integral 0 to 1, x to 1, sine y squared dy dx. So here I'm just giving you a double integral, right? take a quick minute to look at this. Be right back. See what you can do with this. Any issues? Anybody have any issues with that? You should have had issues. Anybody having issues integrating sine y squared? Yeah, you should. That should be a problem. There's no technique of integration that's going to let you get the antiderivative of sine y squared. It's not going to happen. What's that? Some weird error function. Yeah, even if you go to the almighty Wolfram alpha and say integrate integrate sine y squared dy, just to figure out what the antiderivative is. Sometimes Wolfram will time out and say you need to get like the pro version or something, right? So it gives you square root of pi over 2 s, capital S of the square root of 2 over pi y plus a constant. Where it says over here, where s of x is the Frenzel s function, s integral. What the hell is that? Well, it's nothing that we've seen, so it's definitely nothing we're going to be able to do, right? So we appear to be stuck. So what I'm going to do is I'm going to use the limits of integration to draw my region. What is the region of integration in this problem? Well, what type region is this? Since my dx is the outer integral, my x is between 0 and 1, right? And my y values are between x and 1, right? So my top one here, this is really saying y is 1, and this is really saying what? Y is x. So let's graph those. Y equals x looks like this. And y equals 1 looks like this. And we're integrating from 0 to 1 here, right? And we're doing it as a type 1 region in this particular double integral, aren't we? Yes? However, that region could also be integrated using it as a type 2, couldn't it? Could I look at that as a type 2 region instead of a type 1? So can I rotate and do this one instead? What's the, yes or no? Yes? That green one will always be to the right, or, on the side, and then what would be on the left? 0, right? So rewrite this green one, but because it's type 2 now, solve it for x. So it's, pardon me? Because I can, and watch what's going to happen. Yeah, watch. Okay, just if you agree I can do this, this line becomes x is 0, right? And then what are my bounds on y, up and down? 0 to 1 up here, right? So that integral, the way it was presented, was a type 1. But by inspecting the type 1 region, I realize it can be a type 2, and I rewrite the integral as a type 2. So now my new integral becomes, first my restriction on y, which is still 0, 1. But instead of going from x to 1, like up there, I'm going to go from where? What's the bottom one over here? When I say the bottom one, I'm talking about what's this one right here? X is 0. And then what's the top one or the side one? This one right there. What's that one? X is y. Do y'all see the difference? Then we go what? Sine y squared dx dy. Why is that better? What's the antiderivative of sine y squared with respect to x? Well, sine y squared is a constant then, right? So the antiderivative of sine y squared with respect to x would be sine y squared x, wouldn't it? So you could actually do that integration. And let's just see how great it's going to be. So this will be integral 0 to 1. My inner one is sine y squared x evaluated x equals 0 to x equals y. X equals y, and then my outer one dy. Do you all follow that? Yeah? Replacing now x with y, you get y times sine y squared. Replacing x with 0, you get 0. Yeah? So this becomes integral 0 to 1 sine y squared times y. I'm going to rewrite it as y sine y squared dy. Questions on that? Can you integrate that? That's a basic u substitution. U here would be equal to y squared. What's the derivative of u? 2y dy. You have a y dy, right? We didn't have that when we tried it the first way. We didn't have a y sitting out there. Now we do. We have a y dy, which is y dy right here. So if I take this little equation here, divide both sides by 2, I know that my y dy by itself is half of du. So I can rewrite that entire integral. I'm not going to put limits of integration on that integral because I switched to a different variable, so that's why I'm not going to leave it as 0, 1 right now. So this is going to turn into what? Sine of what's y squared for us? U. So that's sine of u. And then what is the y dy replaced with? half of du, right? So I'm going to pull the half out and put the du at the end. What is the antiderivative of sine of u? Negative cosine u. Plus a constant, right? But that's okay. Who cares about the constant? Let's replace u with what it is. What is u? Y squared? That's my antiderivative, right? Now we want to evaluate that antiderivative at 0 and 1. So I'm going to bring this down here. This is equal to negative 1/2 cosine of y squared evaluated at 0 and 1. Plug in 1, you get negative 1/2 cosine 1. Then plug in 0, negative 1/2 cosine 0. What is cosine of 0? 1, so that's just going to turn into, let me see, negative 1/2 times 1. So that's going to be plus a half. So all of this really just becomes, I'll put the plus half in front, then minus 1/2 cosine 1. That's our exact answer. Because when we say cosine 1, that's something on our calculator. We'd have to be in radian mode and just do it, and we get some decimal approximation, but that's the exact answer. Is that okay? Let's go back to Wolfram Alpha for a minute. I want to see if Wolfram Alpha is smart enough to still be able to get this answer. All right? So we want to do that, right? And we want to integrate that from where to where? I'm doing the original problem, the way it was presented to us. From, was it x to 1? From y, from x to 1. Let me just see what it does with that. I think it's really going to have a problem with that. No, it did something here. Okay. So now what I'd like to do, put that in parentheses, and I'd like to integrate that with respect to x from the original problem 0 to 1. That's the right integral, isn't it? Sine squared of a half. It was able to do it. Huh. All right. Now, what I think I'll do now, does everyone have this answer kind of memorized for a second? Right, let's see if ours matches up. 0.2298. What we did is we integrated this, right, but we changed it to a dx here, and we went from 0 to y, and then we went 0 to 1, right? And we went dy at the end. All right? That looks good. If there's any justice in the world, we should get the same answer. We do. Right? Okay. How did they turn into sine squared? Do y'all see that that's just like the power reducing formula backwards, basically, on that? We have a formula, something like sine squared x equals 1/2 minus 1/2 cosine 2x, right? So if I replace my x here with 1/2, I have this, don't I? And then put the x 1/2 here, and that's the answer Mathematica got. So it's the same thing. We have the same answer. think I'll leave that there. Where are my other notes, though? There they are. So the moral of that story is order matters sometimes, right? And there are some problems I'm going to give you out of your textbook for homework where it says, draw the region, change the order of integration, and evaluate the integral. So the whole idea is to draw out the region, and then instead of going type 1, go type 2, or if it's type 2, go to type 1, and see how it makes the integration easier. Hey, when you find stuff at the bottom of your drink, you're like, the hell's that? All right. No, you should always just go after it. And if you can integrate it, integrate it. But if it looks like it's a tough integral, like, okay, this can be like integration by parts or something a couple of times, or, you know, you can tell the integral is going to be a challenge, then go ahead and draw the region and see if you can go to type 2 and see if that would simplify things. I guess the question you could ask yourself is, would integrating with respect to the other variable make it any easier? Like integrating this one with respect to y was not fun. With respect to x, yeah, it would have been pretty clean, right? So there's really no, I wouldn't say just always draw your region before you integrate. I'd say integrate, and if you run into problems, draw it. All right, double integrals, some more properties of double integrals. We had already talked about some of the things you can do with double integrals, like adding them and subtracting them. Constants come out. But it's a pretty cool property. If you have a region, capital D, that is really just a region that's been broken, that you can break up into two separate regions so that the union of those two regions equals D. So you take this set D1, take the set D2, take their union. If that union is capital D, then the double integral over the entire thing is equal to the double integral over just D1 plus the double integral over just D2. Does that make sense? It's like the volume underneath the surface over the whole D should be the volume over just D1 and just D2 added together. I think that's a pretty natural result. That's equivalent to, in Calc 2, when you were trying to integrate from A to B, and you wanted to find the area underneath the curve, you could, if you want, break it up and do the integral from A to C and then from C to B and take those two areas and add them together. It's the same exact concept. Now, I don't know if these examples match up. So let me get my book out. We are in 12.2. Just to make sure this matches up, I'm going to have to take a quick look at my code. Yeah, this is it. This is number 24 from the book. It's just the page number is 708. So I know some of you don't have your book, so I'll just jot down here what we have. It says find the volume of this solid, or the solid enclosed by z equals x squared plus 3y squared, x equals 0, y equals 1, y equals x, z equals 0. So let's talk about each one of these, what they are geometrically. In three-dimensional space, what is z equals x squared plus 3y squared? In 3D, because two of the variables are squared and there's addition between them, it's a paraboloid. Okay, it's like a bowl, right? Plug in x is 0, y is 0, so at the origin you're at 0, and then if you let y be 0, then you've got a parabola in one direction, right? If you let x be 0, you have a wider parabola in the other direction. So what you get is like this bowl-looking thing, but it's like a paraboloid. Parabolas in each direction. Yes? Okay. Then what is x equals 0 in three-dimensional space? It's a plane. It's the YZ plane. So it's one of your walls, right? What is y equals 1? That's like the XZ plane, but it's been XZ, so it's been shifted though, 1 unit. And then what is your y equals x? It's a plane, right? Your z is free, which means that it's a vertical plane. It's coming straight up and straight down, but it's got some sort of angle to it. The angle is given by y equals x, so it's like the diagonal. I'm going to draw all this, but trying to think through these before I draw it. Z equals 0, xy plane's the ground. All right? So let's try first drawing this out in 2D. I'm going to try and draw it on the ground. So in 2D, where is this in 2D? If we're on the xy plane, then z is what here? 0. Which means the only way this is going to be 0 is what? It's the only way this thing right here can be 0. If they're both 0, right? Remember that paraboloid comes and touches at the origin? So the only thing that this is in our plane is just a point. It's the origin. That's it. It's the bottom of the paraboloid. X equals 0, we said was the ground, right? So it's just, I'm sorry, not X, I meant to say Z. X equals 0 is the y-axis, right? Yes? This is X is 0. Y equals 1. Here I was bragging about my straight lines. That's y equals 1. Y equals x, the diagonal. And z equals 0, that's the ground, right? But so I can't account for that here. I mean, it is what I'm looking at. It's the ground. All right. Do you see the region that's enclosed? Do you all see it? This is going to give us what type region we have, right? The question is, what is it that we're finding the volume of, though? I mean, we have the paraboloid, right? We have the paraboloid coming up like this. That paraboloid just keeps going. We're trying to find the volume between that, the ground, which is z equals 0, and then these three planes. Remember, these planes come out at us, right? They come out three-dimensionally, come straight out, So they come up and hit the paraboloid somewhere, don't they? It becomes difficult to visualize, which is why I try and put this together. Here's our paraboloid, right? Was that our region on the ground? My region is... Why does my region look like that? Maybe I used a different function. This is supposed to be the y-axis. Turn things. Maybe I used a slightly different variation of the problem. So there's x equals 0. Do y'all follow that? That's x equals 0. I thought this projector was like really badass. What happened? I mean, my colors are too close to each other. That's a little better. Right, that's x equals 0. That's the ground, right? That z is 0. This is x equals y, or y equals x. I can look at it from the top, right? It's y equals x. And then, what's this one? Y equals 1. Which was this one, y equals 1. Do you see them all? X is 0, y equals x, y equals 1. And then you have the paraboloid and the ground. So the region we're looking for, you tell me, is it above the paraboloid surface or below the paraboloid surface? It's below, right? Because those planes are cutting off the sides. The paraboloid is the top, and the bottom is what? The ground, right? Z equals 0. So the solid we're looking for is in here. I'm going to pull everything out. Trying to rotate it to a place where you can kind of see. Yeah, you can kind of see it there. I don't know. Can you kind of see the curvature of the paraboloid in here? Like scooped out? And then it's that paraboloid and it's down, but on top of that triangle. Now this is important because what we have is we have a region on the bottom, right, which is either type 1 or type 2. And then, remember, we have to have an upper function and a lower function, an upper surface and a lower surface. In this case, our upper surface is the paraboloid. The lower surface is z equals 0. It might be later that you wanted, let's say you wanted the region bounded by all of these, but instead of z equals 0, you said z equals 5. So now what you're doing is you're putting your z on top, and so you're looking at the paraboloid here, and you're looking below z equals 5 down to the bottom is now the paraboloid, so you're looking above it. Does that see the difference between those two? Do y'all understand the difference? Okay. All right. So what type region do you want to go with here? Type 1? Sure. Here to here? So I can start setting up my double integral, I think, just by looking. Since it's type 1, I have restrictions on x. What are my restrictions on x here? Does that look like 1 there to you? Or it is 1, right? We don't have to do a lot there. 0 to 1. What's the bottom one here? Y equals x, right? So I'm gonna put x down here on the top. What's the top function? Y equals 1. And then I'll put my order of integration. It's going to go dy dx, right? Here's the part that requires the little bit of thinking. It's kind of like it's your top surface minus your bottom surface. For us, the top surface was the paraboloid, which means you have to be able to describe the paraboloid as a function of x and y. But just replace z with f of xy, right? So this is the actual surface of the paraboloid. That's our top. So we can just put x squared plus 3y squared. And then minus what? What's the bottom? 0. I'm going to put it there just so we see it. And then we just go ahead and integrate that. Are we going to run into any problems integrating that? You think? No? Yeah, we won't have to worry about changing to a type 2 because those are all polynomials. Those should be pretty clean. Okay, number 28 from the book. Same thing. Find the volume of the solid bounded by x squared. No, not x squared. Y squared plus z squared equals 4. Z equals 0. Shit. No, I keep on looking at the wrong line. Sorry. Y squared plus x squared equals 4. x equals 2y, x equals 0, z equals 0 in the first octant. Remember, there were 8 octants, right? The first octant, your x, y, z are all positive, right? So what is this stuff? Let's try and think three-dimensionally. What is y squared plus z squared equal, or sorry, y squared? I don't know if that was plus or minus. Let me look back in the, I think that was supposed to be a plus. Yeah, it's plus. Sorry. What's y squared plus z squared equals 4 in three-dimensional space? Okay, a paraboloid would require that we have 3 variables in there. That way, if like y and z were both 0, then your x would be 0. But see, we're holding here the 4 is constant. Cylinder, good. It's a cylinder. It's cylinder because it's almost like x squared plus y squared equals 4, which is a circle with a free variable. Here we have y squared plus z squared is 4, which is a cylinder. What variable is free? X. So this cylinder goes down, runs parallel to the x-axis. Now, we did this a long time ago, so I realize this is like way back then. But you should know you might need to flip back to that section and be like, okay, what do these things look like? So I know that this is a cylinder. It has a radius of 2. It runs parallel to the x-axis. So if I were just drawing out loud, drawing my ideas out loud, if this is x and this is y and this is z, I know that this thing does something like this. And I know it hits here at 2, and then up here, up there, it hits at 2, and then over here, you know, curves back down. Hits. Y'all understand? Down the x-axis, you got the cylinder. Actually, that's not a bad drawing. All right, that's what that looks like in three-dimensional space. What does this look like in three-dimensional space? X equals 2y. Plane, right? And this plane, because z does not appear in the equation, the plane's straight up and down, but it might have some sort of rotation to it. And that rotation will follow whatever that slope is, right? X equals 0. It's the y-axis, or it's the yz plane, straight up and down. And then z equals 0. It's the ground. So let me try and get my 2D picture of what's happening. In my 2D picture, right? In my 2D picture, what does this become in my 2D picture? Y squared is 4, right? Y squared is 4 because z is 0 on the xy plane. So if y squared is 4, that means y is either positive 2 or negative 2. But we are in the first octant, which means that we are actually only positive 2. Do y'all agree? If we're in the first octant, we're really only in the first quadrant? That's kind of a big deal, right? If we're in the first octant lies on top of the first quadrant in two-dimensional space. So I really only need to consider y equals 2 here. That's 2 there. And that's coming from, that actually comes from the idea that y squared plus z squared equals 4, but z is 0, right? So I'm kind of jotting that down. Doesn't help when you can't read it, but right, this y equals 2 comes from taking this equation, letting z be 0. All right, what does x equals 2y look like? It's a line. Slope is what? 1/2. So I go up 1 over 2, up 1 over 2. Crap, my picture's going to suck. I'm going to save myself here. Here's what I'm going to do. I'm going to move my x-axis up a little bit. So up 1 over 2, put me like that. Now I can continue extending these, right? But I'm just going to keep in mind that the only thing I'm going to be focused on is going to be in this first quadrant, because if I'm in the second quadrant or third quadrant, I'm in different octants. And then x equals 0. This one was y equals 1/2 x. X equals 0 is this vertical y-axis like this. Z equals 0 is the ground, right? We have the region though. Type 1, type 2. What do you like? Type 1? Stick with type 1, man. If it works, it works. Type 1 here. I do need to figure out my restriction on x. I know it starts at 0, but where does it stop? So where does 1/2 x equal 2? At what x value? At 4. All right, if I set 2 equal to this, I get 4. So I know this x value is 4. Y'all okay with that? So my double integral is going to go from 0 to 4, right? And then I'll have my bottom function is the red one here, so that'll be 1/2 x. I'll integrate from there up to where? The top function, which is constant. It's just 2. Yes? So integrate 0 to 4, and then I'll integrate from 1/2 x to 2, and then the all-important part of this. What is it that I'm integrating? We had those two walls coming up, or what did we have here? We had this wall coming up, right? This wall coming up. This is not a wall, though, that blue part, right? That blue part is actually where this curved cylinder comes down and hits the XY plane. So what is above the solid we're looking for is that curved part, right? And below it, down to the XY plane. So the top surface is actually the cylinder, right? So we have to take the cylinder and we have to solve for which variable? We have to make it a function of x and y. So we solve it for z. When you solve that for z, what do you get? Z equals plus or minus the square root of 4 minus y squared. And I'm only going to take plus because I'm in the first octant, right? So that's our function. D what? D what? dy dx? Yay or nay? Well, I said that it had to be top minus bottom. What was bottom here? 0, the ground, right? Z equals 0. Could you integrate that? There's probably a formula in the back of the book for this off your table of integrals, but you could also use trig substitution, trigonometric sub. Would changing the order of integration make it better? What do you think? I'm asking you, I'm just curious. Integrating this with respect to y right now is tough because it's not clean. You have to do trig sub or table. But if I integrate this with respect to x, then an x is going to pop out, right, when I integrate? And then I'll plug in these limits of integration, and most likely, because these are linear, the new limits of integration will have like a y in there. And if I had a y out in front of this, then I could do a basic sub to do it. So I'm thinking here a changing of your limits of integration would make it easier by hand. But that you just have to go through. Either way, you could do this one either way. That sine y squared example we did, you could not do the sine y squared. So our geometric situation, here was our region, right? Here was the YZ plane. Oh. No. Here's our cylinder, right? There's our cylinder. Here's our YZ plane, so that's x equals 0. That's our y-axis, basically. Here's that diagonal, or no, that's z equals 0. That's the ground. Okay. Then we have the, what was it, x equals 2y, which was, remember, we're looking like that. There's the y-axis, here's the x-axis. So there's our diagonal plane. But I'm turning it so that we can look at it this way. Stop it. And so we're looking for the region that's enclosed by all of those. So this plane, this back wall, this bottom, and then the cylinder. You see it? Whoa! I heard a crunch there. So here's our solid. It's this piece right here. We pull all this out of here. Okay? I'm not going to take that any further. Okay, so what did I assign last time out of this section? It was very minimal, wasn't it? What was it? 11 and 12. Okay, so now, in addition, on page 707, you know, some like 15, 17, 21 through 29 odds. These are good problems. These right here are pretty much like the last two I just did. So you have to kind of be able to visualize what's happening, which is somewhat of a challenge, which is why they're good. I think that 37, oh wait, no, not 37, 43 through 47 odd are also good. Those problems, it says evaluate the integral by reversing the order of integration. So this is where you have to draw your region, switch everything over, and then redo the integral. That's a good set of homework right there for this section. Next time when we meet, we will get into polar coordinates. Polar coordinates, so we'll be doing double integrals using polar coordinates. Wanted to see where we were on our calendar. You're wanting your take-home quiz, right? Yeah, I'm going to email it to you later today. I didn't quite get it done in time, so I'll email it to you. All right, and I'll let you know when you get it. What time? Are you disappointed? I'm sorry. I'll let you know when it's due and stuff. So where are we as far as date? Ooh, how did we get so far behind? $12.3, $12.4, $12.5. My goodness. We'll have a little bit of ground to make up. We were supposed to finish 12.4 today. What happened? How did we get so far? I took a lot of time on, I guess, these first two sections. But 12.4 will go pretty quick, so I'm not too concerned about that. 12.5 will go pretty quick also. Because, well, maybe not. let's just see how it goes, all right? Do your homework. That's all you can do, right? Do your homework, study. If y'all know anyone else in